Timberborn is a city-building survival game, but what really separates it from other games in the genre is its water. Water is central to Timberborn. You need it for crops, you need it for drinking, and you need it to power your industry. A lot of this game centers around making increasingly more advanced dams and waterworks to manage this supply of water. But the mechanics of water can sometimes be confusing and can lead to problems. In this video, we're going to cover everything about water as of Update 6. We're going to go from the basics to all the more advanced rules so you can level up your Timberborn builds. Even for the most seasoned players, there should be something new in here. Let's start with the basics. Timberborn has two types of water: good water and bad water. Good water turns the world green and is vital for your crops and beavers. Bad water pollutes, kills crops, and makes beavers sick. However, bad water is also vital as an input to your heavy industry. Good water and bad water can be mixed together, and this results in water at different contamination levels with mixed effects. Bad water comes from bad water sources, while good water comes from good water sources. During droughts, both types of water sources will turn off, requiring you to survive on whatever water you've stockpiled in your dams and tanks. Occasionally, you'll run into a bad tide, and these are special seasons where all sources of water on the map will start to produce bad water. An unprepared colony can easily be destroyed by a bad tide, polluting vital waterways and killing all your crops. In the game, it's common to make bad water diversion systems, and these are systems that will redirect that bad water during bad tides. Good water irrigates, bad water contaminates. As long as water is less than 50% contaminated, it will irrigate the nearby soil, turning it green and making it possible to grow crops and trees. There are some complex rules that determine exactly how far irrigation will reach, but generally the less contaminated the water is, and the wider the source of water is, the more tiles will be irrigated. Usually a 3-wide channel will irrigate the maximum range of 16 tiles away. Differences in height can also affect the irrigation range. Each step the soil is above the water will reduce the range of irrigation by 6 tiles. So deep channels may not irrigate nearby soil high above them. Steps down in height, however, still irrigate at the full range. Soil contamination happens when the water is contaminated by at least 50%, and it will go up to 7 tiles away. This contamination will kill all your trees and all your crops. Similar to irrigation, steps up in soil will reduce the range of contamination, while steps down will not. For example, this means that you could dig a deep ditch for bad water, and you could route that through greenland without resulting in contamination. Both factions offer buildings, called barriers, that can be used to affect irrigation and contamination. The folktales get contamination barriers, and these are barriers that stop the effect of contamination but still allow a positive effect of irrigation. The Iron Teeth, however, get irrigation barriers. These barriers stop both contamination and irrigation, which can make them slightly harder to use. Both barriers must be built on dry soil, so you can't just build them at the bottom of your river. Also, keep in mind that contamination and irrigation can go around these barriers, so even small gaps in your barriers can cause contamination to slip through. Water in the game will slowly evaporate over time, which will eat into your supply during droughts. How fast your water evaporates is a little counterintuitive. As you'd expect, the more surface tiles your water has, the more evaporation you'll get. However, there is also a multiplier based on how many adjacent tiles are also holding water. The more water that is nearby, the lower that evaporation will be. There is a severe penalty for single tiles of water in 1-wide canals. As of Update 6, the sweet spot to minimize the effects of evaporation and to maximize the effects of irrigation is a 3x3 pond or a 3-wide canal. Both good water and bad water can be pumped out of your rivers and lakes. This is the only way that they can be used to drink or as input to the other industries. Regular pumps collect good water, while bad water pumps collect bad water. Both pumps can work in mixed water supplies and will only collect the type of water that they're meant to pump, but at a reduced rate. For example, you can successfully pump drinkable water from contaminated water without your beavers getting sick, provided there is at least some good water in there. Pumped water is stored in tanks. Tanks have two very important properties. First, they are not affected by evaporation, making them a good option for long-term storage of drinking water. Two, beavers have somehow discovered how to compress water, and a tank is able to store significantly more water than the equivalent size in the open world. For example, here you can see a medium and large tank and the equivalent amount of water they would hold in a regular dam. You can uncompress your tank water and put it back in the world using a building called a fluid dump. A fluid dump is relatively low throughput and, just like a pump, needs to be operated by a beaver. However, it can be very useful to irrigate hard-to-reach areas. A 3x3 pond is your best bet to maximize irrigation and minimize the effects of evaporation. By the late game, both factions have options for capping off bad water sources. The Folktale get two buildings. The first is a dome that allows you to seal off a bad water and prevent it from flowing. The second is a rig that also stops the flow of bad water, but allows you to pump large quantities of bad water directly from it. The Iron Teeth get a bad water discharge. This is similar to the dome, but with one key exception. It allows you to force bad water to keep flowing even during droughts, and this can be used to have a reliable source of water power. The primary way that you control and collect water in the game is by building dams. In the early game, you really only have access to two basic building blocks: a solid levee block that lets you stop water, and a simple dam block that lets you retain water up to 0.7 height and lets everything else flow through. This should let you build some pretty basic dams. Beyond these, there are two vital blocks that allow you to further control water: floodgates and sluice gates. Floodgates are like the regular simple dams, except you, the player, get to dynamically control the height of the water it will retain. You can use this, for example, to manually close waterways during bad tides, or to slowly release water from upstream dams to keep downstream areas topped off. Sluice gates are new in Update 6 and are one of my favorite blocks. They allow water to flow through in a single direction and can be configured to automatically open and close based on the height of water downstream, up to but not beyond their own height. You can use this to always keep downstream water at a specific height without needing to do manual work. They can also be configured to automatically open and close based on the contamination level of upstream water, allowing you to make a fully automated bad water diversion system. You can think of floodgates and sluice gates as two sides of the same coin. Floodgates let water through based on the water level upstream, while sluice gates let water through based on the water level downstream. You're commonly going to use both paired together in your dams. Sluice gates at the bottom will let you keep downstream areas topped off as needed, while floodgates or dams at the top allows for overflow water to escape in a controlled manner. You'll also often pair sluice gates with either more sluice gates or floodgates downstream to retain the water that your sluice gates are releasing. When you do this, you need to make sure that your downstream gates are configured to retain a water height at least as high as your upstream sluice gates are set for. Otherwise, your upstream sluice gate will never meet its closed condition and it will remain open, draining your entire dam. Now it's time to get into some of the more advanced stuff. Flow rate. Water flow rate in the game is measured in cubic meters per second, or CMS. Every water source in the world has an associated CMS. Knowing the CMS of a water source is very useful for planning the rest of your system to prevent overflowing and to maximize power generation. The CMS will ramp down when a drought begins and will ramp back up when it ends. It can only be read directly in dev mode, but in the game you can still measure it using a water gauge. Keep in mind that the CMS of a river is distributed across the entire river width. So to get an accurate reading of the entire river, you either need to build multiple gauges and sum the CMS that each reports, or narrow the river and measure once. With some catches that we'll get into soon, a single tile 1 deep can handle a little bit over 6 CMS of water without overflowing. You can make rivers deeper or wider to support more flow. For example, a 2 deep canal or a 2 wide canal would be enough for 12 CMS. You can also use this to estimate how much space will be taken up by smaller currents. Sometimes, when there is a sudden change in water flow, you might get temporary overflow as water sloshes around. You might have to wait a few seconds for the system to stabilize. As I mentioned earlier, the total CMS of a river gets distributed across the width of the river. Narrowing or widening the river allows you to increase or decrease the CMS for a single tile. Widening the river slows it down, while narrowing it speeds it up, because you're forcing more water to pass through a single point. Narrowing the river to increase flow is an extremely powerful technique when building water wheels to generate power. Water wheels generate more power the faster the water is going through them. Internally, they have a base power that is multiplied by the CMS that is flowing through them. For example, instead of having 5 water wheels with 1 CMS each, you could narrow the river and build only a single water wheel. Both these setups are generating the exact same 300 horsepower, while one costs significantly less to build. A common technique is to take advantage of this by creating a narrow canal in a snake-like pattern that concentrates your CMS, and then to fill it with a bunch of water wheels. Flow rate is also vital for planning waterfalls in your rivers and waterworks. Water can freely flow upward and left and right with no restrictions. However, every time water flows downward, it is limited to 2.2 cms per edge of a waterfall. If you don't have enough edges in your waterfall, you get flooding upstream because you've created a bottleneck in your river. This is by far the most common problem that I see people run into when they have flooding in their lines. You can easily work around this by introducing more edges into your design to accommodate the total CMS of the river. For example, here I've got 3 CMS of flow, and when I added a levee, I started to create flooding. That's because I only have one edge, allowing 2.2 CMS through. By moving the levees around, I can create 2 edges, allowing for 4.4 CMS of flow and resolving the flooding. With just a few levees, you can modify your waterfalls to handle extreme volumes of water. For example, here's a waterfall trying to handle 24 CMS, way more than you'd probably ever see in the game. By only introducing 2 columns, we're able to create 14 edges, and that's more than enough to handle all this flow. Finally, a lesser known technique to get around this is known as waterfall stacking. Each dam and sluice gate produces its own waterfall. Each of these waterfalls gets its own 2.2 CMS limit. By stacking them vertically, you get more edges, allowing more flow through. Prior to update 6, I've also heard that you were able to use waterfall edges in a technique sometimes called magic tiles to get around that 6.6 CMS per tile height limit. Unfortunately, in update 6, I haven't been able to recreate this. While on the topic of CMS and the required tile height, there is another catch I've noticed. When water flows from one tile to another, there must be a very minor height difference. Over small distances, this is almost imperceptible, but over long distances, you can start noticing it. This is especially true if you start making those snake-like pattern canals to stack multiple water wheels in a small area. When water flows over long distance like this, the bottleneck downriver has its height determined by that 6 CMS per tile height guideline I mentioned earlier. Every tile upriver from here must be ever so slightly higher. This has an interesting side effect. By making a river longer downriver, you can actually cause flooding upriver. For example, here you can see that I have 6.2 CMS of flow over this one deep canal, which is just at the limit of what it can handle. If I make this canal just slightly longer, we suddenly get flooding up at the source. This also means that speed bumps in your river can cause all tiles upriver from that point to increase in height. For example, looking at this river with 3 CMS of flow, it only requires 0.3 height. If I were to create a speed bump in this river about halfway through, I've reset the height requirement to always be increasing from the top of this levee backwards upriver. Every point upriver must now be slightly higher than it. This change in height per tile appears to be dependent on the CMS of the water going through the system, and I haven't identified an exact calculation yet. I'm roughly seeing 1 tile increase in height gained over hundreds of tiles, with the higher the CMS, water gaining height over shorter distances. Unless you're trying to maximize flow rate through compact designs or doing crazy snake patterns, you might not even run into it. If you are making these long snake patterns for power plants though, you'll need to account for the height difference by staggering the height of your water wheels as you get farther and farther upriver. As of update 6, we now also have support for 3D water. This allows us to build both aqueducts and pipes. The key building that allows all of this is the impermeable floor. The impermeable floor can be placed on top of any solid building, such as platforms, overhangs, warehouses, and homes. When present, it prevents water from flowing through the floor in either direction. You can build aqueducts by placing impermeable floors at the base, followed by levees on either edge. Aqueducts work just like regular rivers, and the same flow rates and waterfall restrictions apply that we've already talked about. Pipes are formed when you completely seal a canal of water with impermeable floors on the top. When bodies of water are connected this way, they can actually transfer water until they equalize at the same height. This is known as communicating vessels. It's the same idea behind real-world water towers. For example, you could build 2 dams high up on the map, connect them with a deep underground pipe, and water will transfer and equalize at the same height. Pipes can also be used to push water upwards without needing any mechanical fluid pumps. When a source of water is completely encased within a pipe and there is nowhere else for that water to go, it will start pushing water upwards within the pipe. For example, in my Steel Tide series, I was able to use this to cap water source at one end of the map and actually fill another dam on the top of a mountain on the other side of the map. Pipes are also the only way I know to get around that CMS per tile limit we were talking about earlier. When a source is completely sealed, I've found no limit to the amount of CMS a 1x1 pipe can transfer. For example, here I've got one pipe carrying 32 CMS of water. However, a big catch with pipes is they are still limited by that 2.2 CMS limit whenever water needs to go downwards. It's very easy to accidentally introduce a bottleneck into your pipe without realizing it. Finally, keep in mind that water in pipes is still affected by evaporation rules, and a one narrow pipe still gets those stiff evaporation penalties. Alright, we've seen a lot of rules, guidelines, and mechanics. Let's take a look at how you can combine all of this knowledge with some practical examples. First off, one of the most common patterns you'll see is narrowing your river to maximize your power from water wheels. Provided the river is deep enough for the current, you can get some extreme power from only a few wheels. Here's a basic example of using sluice gates to redirect bad water during a bad tide. You can see the water gets redirected without any direct intervention. In this example, we have a fully green tree farm and lake. However, underneath it is actually a bad water pipe. Because the bad water pipe is so far below ground, the surrounding dirt is not contaminated. During the bad tide, this one pipe is able to handle over 9 CMS of bad water. Here's an example of using a pipe to transfer water across a valley and up the other side without needing to use any mechanical pumps. Using communicating vessels, both will equalize. In this example, we've got a water wheel that just can't reach the water below. By introducing a speed bump slightly downriver, we can increase the height of the water upriver, letting the water wheel start working again. Finally, here's an example of a dam overflowing because the waterfall is a bottleneck. We are trying to force 12 CMS of water through a dam only capable of handling 8.8. By adding just 2 more dams, everything is resolved. These are just a few examples. Once you know the general mechanics, you can build all sorts of different waterworks. I hope you find this video useful and it lets you build all sorts of crazy things. Have fun, and I hope to catch you next time.